All right, welcome back to Codex. Alex Cloninger is an assistant professor in the Department of Mathematics at UCSD. He studied with John Benedetto and Wojciech Shaya at Maryland and received his PhD in 2014. He did an NSF postdoc at Yale with Rafi Koifman before joining the faculty at UCSD in 2017. Alex's research revolves around fundamental ideas in mathematical data science, including diffusion geometry, optimal transport, and deep learning. Today, Professor Cloninger will speak to us about distances between families of distributions. Take it away.
Awesome. So thank you so much for the invitation. And this is a lot of fun. This is actually the first of these virtual seminars that I've given. So apologies if I'm a little rusty. This is sort of a interesting format. So yeah, so today what I'm going to be talking about is basically different ways to define distances between distributions and how this connects to a lot of other types of mathematics and how you can make improvements both computationally and theoretically. So this is joint work with several people, my colleague Xian Cheng, who I work with a lot, Rafi Koifman, Rishikesh Maheshkar at Claremont Graduate University. And I also want to shout out that for the optimal transportation part, this is work with Caroline Moosmuller, who's a postdoc at UCSD and is actually on the job market this year. So just making that as a quick plug. Okay, so what are the questions that we're actually going to talk about? So the main sort of central question that I'm interested in recently is, suppose you have some data points sampled from a distribution. You have some data points sampled from a second distribution. Those distributions are on RD or something simple. And you want to ask a simple question. Did those come from the same distribution or did those come from different distributions? Okay. And at its core, this is a statistics question, right? This is the two sample test. I am not a statistician. You guys are not really necessarily statisticians. Maybe there are some statisticians here. So what I want to emphasize is that while this may seem like a statistics question, there are really deep-rooted ideas here in spectral theory and harmonic analysis, geometry, commutators of group actions we'll get to when we talk about the optimal transport part. And quite frankly, this is a very important problem in data science and machine learning. I'll hopefully motivate that with some interesting applications. But what I want to do is break it up into a couple of additional questions that aren't just the classic statistics question. And then we'll sort of talk about how we're going to address these in various ways. So another question that I'm really interested in is, all right, what if you didn't just have two distributions? What if you had, n distributions? And you wanted to compute all pairwise distances between these distributions. This actually becomes a very computationally difficult question because each distance that you're going to compute between two point clouds is usually pretty expensive, which means if you have n clouds, then you have n choose two expensive computations that you have to run. And that can be really prohibitive, okay? I want to motivate why I care about these problems a little bit. And we'll delve especially into the flow cytometry one later, but just as an example, flow cytometry is a medical test that some colleagues of mine know a lot more about than me, but I'm going to talk about it in this, in this discussion. Basically, what it is you take somebody's blood, you treat it with some chemicals, you drop it cell by cell, shine some light on each cell. Each cell now gets some representation in like 9 dimensions. Okay, and in that 9 dimensions, by the way, sorry, I see that there's like okay. I see the chat flashing. I want to see if there's any questions already. So anyways, in flow cytometry, now what you get is a person who's represented by basically a 50,000 point cloud in 9 dimensions. So the question is, how similar is my point cloud to your point cloud? Because this is actually a really important way to be able to detect whether or not you have some blood disease or cancer, or leukemia, something like this, okay? Anytime you hear anything about generative models, at the end of the day, they're actually just computing some 2-sample testing problems. Because what they're doing is they're saying you have your data, you have the data you've been able to generate, how close do those distributions overlap with each other, okay? And this could be true for trying to talk about subpopulations of patients. There are a lot of different applications for this to show up. Another question that I'm really interested in, again, related to this, is not just whether they deviate or how much did they deviate by, but I want to figure out an indicator of where each distribution dominates. So let's say that both distributions have some density associated with them, so they're absolutely continuous. I want to figure out, okay, for this red and blue distribution, all right, red is actually dominating over here and blue is dominating over Why is that relevant? Well, because this is actually going to be some sort of interpretable way to talk about why a decision was made that these point clouds differ. Right? I want to be able to say, oh, here's a function that says this is really where one distribution dominates. That's probably the sort of characteristic part of that distribution. Okay. And finally, what I want to talk about is so that's all unsupervised problems, clustering, things like this. I want to actually talk about supervised learning on the space of distributions as well. Okay. And so here, this is a slight variant of your traditional supervised learning problem. You don't just get a data point and a label associated with that point, but you actually get an entire cloud of points and a label associated with that cloud. And that cloud came from some distribution. And the question is, how do you actually build a function that takes in the distribution or the samples from the distribution and outputs classification? So again, this is relevant to the flow cytometry problem because you have this situation where you might want to say, do they or do they not have repeat? That is a supervised question. But also this could be true if you think of images as being distributions, right? A 7 is really a distribution on the unit square. So if I want to be able to build a classifier on that distribution, I want to be able to say that is in fact a 7, right? And similarly, I want to be able to think about building invariances into this. So what if I want to not care about whether a distribution is sheared or shifted or scaled or something like this and still be able to recognize it as a type of distribution? Okay. So those are kind of the motivating questions that I'm interested in. And I'm going to focus on two main algorithms. These are pre-existing algorithms. I'm obviously not the person who created either of these. And we'll delve into more detail in both. But the two main things I'm going to focus on are one that's called maximum mean discrepancy, and another that maybe a lot of you have heard of before, which is optimal transport, or Wasserstein-2 Distance. Okay. So these are two very classic ways to talk about distances between distributions, but they have fundamental problems. Not fundamental, but they have real problems. For one, if I have n distributions, computing all n choose 2 distances is incredibly expensive. Okay, it's gonna, each one of these computations, MMD is very memory intensive. Optimal transport involves solving some sort of linear programming problem. Doing that n choose 2 times is really hard. Second, the complexity of these algorithms is more or less independent of the family of distributions I'm interested in. In other words, if I just have a distribution and shifts of it, and I want to say how far apart they all are, it's going to be just as difficult in computation as if I had, n really complicated distributions that were really subtle differences. So there's no scaling associated with how complicated the distribution is. And the third thing is that neither of these inherently lend themselves to some sort of nice Euclidean or Hilbert feature space where you could just take some off-the-shelf supervised learning algorithm and say, oh, that distribution is, a 1, that distribution is a -1. Okay. So these are the main kind of questions that I'm interested in. And basically what we're going to do is we're going to start talking about how we can make assumptions that will actually make the problem easier. So rather than thinking about all possible distributions, we'll think about a geometric assumption, which is that those distributions are concentrated on or near some low-dimensional manifold. Okay. Or you can make some algebraic assumption, which is that all of your distributions actually came from push forwards of a particular distribution. Right? You can think of like shifting a distribution, scaling a distribution, shearing a distribution, things like this. Okay. And that all of those push forwards are maybe some subgroup. Okay. Or some group. And we want to think about how complicated the problem is as a function of that group. Okay. And our goals at the end of the day are going to be able to create some feature space to be able to do learning. We want to be able to talk about unsupervised learning. So once you have some nice embedding of a distribution into a Euclidean space, you can do things like just Euclidean distance to be able to define clustering. You can do supervised learning. You need to have some sort of out-of-sample extension. These are the main questions that are kind of interest. So what I'm going to do is highlight a couple of examples where we can address parts of these questions and hopefully kind of motivate more questions. So the first is about maximum mean discrepancy. And what I want to describe real quick is one slide, just what is maximum mean discrepancy and how does it work in its sort of most straightforward form. Okay. So we're going to specifically talk about kernel maximum mean discrepancy I'll explain that in one sec. But basically, what it is it's like a total. If you have two densities, P and Q, maximum mean discrepancy is the maximum over all functions, or the sup over all functions in some function class of f inner product with P minus Q. So effectively, it's like the total variation of P minus Q. You're basically saying, I want f to highlight where P minus Q is as big as possible, right? And I'm able to hone in my f on that region. Okay. And this is actually a pretty good test because, in particular, if P is equal to Q, then obviously you can't do it anywhere, and this will be true. So this has been around for a long time. I think a lot of discussion about maximum mean discrepancy showed up in '94 with a paper by Anderson. In 2012, Arthur Gretton came along and basically said, oh, what if our function space was that of a reproducing kernel Hilbert space? Okay, so what if I don't think about functions from continuous functions or Lipschitz functions. I think about functions that are in the ball inside a reproducing kernel Hilbert space. Well, in that case, you get this really beautiful result that says that you can basically get rid of the optimization part because the f that maximizes can be written down explicitly. It can be written down as basically the kernel inner product with P minus Q. That is your function, and then you apply it to P minus Q. And this is the maximum mean discrepancy between two distributions using some kernel, okay? And the beauty of that is that there's a nice discrete version of this. If you broke this up into the discrete case where you were only working with, n samples from P and n samples from Q, that would basically break down into what is the average affinity from points in X with other points in X? What is the average affinity from points in Y with other points in Y? Minus twice the average affinity of points from X and points from Y. So you're saying how self-similar is X to itself? How self-similar is Y to itself? Minus how similar X is to Y. And if those are all on the same scale, this is basically 0. If they're on different scales, this is non-zero. And there's some notion of distance. Okay. And there's been a number of papers that have come out since then, usually from Gretton's group. Bernard Skolkoff has worked on this as well, Alex Smola, several others, that establish various results about this. Okay. So what I want to think about, because I come from this from a harmonic analysis background, from a manifold learning background, is really this is actually kind of like a manifold learning problem. Okay, and the reason is the following. If you think about the maximum mean discrepancy, so it's basically this double integral of kxy, difference distributions, and you think about the eigendecomposition of k. Okay, you don't actually have to compute it, you can just sort of think about it theoretically, right? Then the MMD is really just the sum over the eigenvalues of the k times how much energy you get from projecting P minus Q onto one of those eigenfunctions. So if you have an eigenfunction with really large eigenvalue, and P minus Q projects onto it non-trivially, then that contributes a lot of weight. That says, oh, these things are variable. If it projects 0 onto most of the eigenfunctions and only non-zero onto eigenfunctions with really, really, really tiny eigenvalues, then it's not very useful. Okay. And the reason that I bring this up is because thinking about the eigenfunctions of a kernel, this ties back into sort of classic manifold learning theory. Okay. You can say a bunch of things about how like the eigenpair of the kernel is the bandwidth of your kernel goes to 0, is tied to the intrinsic geometry of the manifold, related to the manifold of Fauchen. You can talk about how when the number of points is large enough and the bandwidth is small enough, you can basically spectrally approximate this. Everything really boils down to the spectrum. Okay. And basically what I want to say is spectrum, if you get anything out of this part of the talk, it's that spectrums of kernels are weird. Okay. And we'll talk about how to sort of craft our spectrum so that we can get a better test. Okay. So why are spectrums of kernels weird? Well, it depends a lot on the geometric structure of your data. So for example, if I had, say, my domain or sort of the support of P and Q was concentrated on some long rectangle, what are the eigenfunctions of this kernel wind up with? Well, the first one varies in this direction, the second one varies in this direction, varies. They're all varying left to right. In this example, I think you're going to have to go to like the 16th eigenfunction before you get something that varies up and down. Okay. So why is that a problem for the statistics test? Well, it's a problem because that means that if P and Q deviate in the vertical direction, you're not going to notice that deviation until you're really, really, really deep in the spectrum of the kernel. And that's a problem because now you're not going to give a lot of weight and you're going to pick up a lot of noise from maybe statistical deviations that weren't really meaningful in the horizontal grid. Okay. So there are ways you can fix this. For example, what if I, instead of thinking about an isotropic kernel, thought about an anisotropic kernel, something that rescaled? Okay. So if I knew how to rescale this, you know, this is 8 times as long as it is tall, and I look at the eigenfunctions of the rescaled kernel, then my eigenfunctions are actually going to vary in ways that will pick up vertical and horizontal differences quite easily. Okay. By the way, this is still on this original domain. I'm just sort of plotting the rescaled version of it, rescaled by, you know, the covariance matrix A1. So rescaling actually has a lot of benefits. And that's kind of going to be the idea here. Okay. I want to give another example of why this is important, but related to the actual maximum mean discrepancy problem. Say I had 2 point clouds, they're the blue cloud and the green cloud, and I want to detect whether or not they're from the same distribution or not. This is what I would call an off-manifold deviation. I have this nice clear behavior of blue, this nice clear behavior of green. It's very obvious from looking at this, these two are different because green is almost always above blue. But if I use an isotropic kernel and I look at eigenfunctions of that kernel, you get eigenfunctions that just keep varying along the curve. You're never detecting the off-manifold behavior. But if I created an anisotropic kernel and did the same thing, and specifically what we're going to call locally anisotropic kernel, I'll define that in a moment. But basically what it means is I just build covariate, I build sort of a ball for my Gaussian around this point that is not isotropic, but is instead varying in some direction. By the 7th eigenfunction, I'm really picking up off-manifold behavior. By the 8th, I'm saying, all right, if P minus Q, you know, is concentrated here or here, like I'm very quickly picking up that there's going to be some difference. Okay. And that will make for a more powerful test. So let's say what the test is first, because this is all about spectral theory, but in reality, you don't need eigenfunctions. Okay. You prove everything with eigenfunctions, but in computation, you don't do it. So I'm going to make an assumption here. This might be a little bit of a bold assumption. We'll talk about how to, you know, justify it a little bit forward. But imagine that you could take your ambient space and get some what we're going to call local geometry. Basically, what I mean by that is we're going to pick some reference points around our space, hopefully that are near our data. And around each reference point, we're going to give a little covariance matrix. That little covariance matrix can be made through like a local principal component analysis. Okay. You can sample R from X union Y, you know, the 2 data sets. They can be a random subsample. You can do quadrature methods. You can do, you know, some sort of nice skeletonization of all of your point clouds, whatever you want to do. Sigma comes from nearest neighbor, from a covariance of nearest neighbor. And then what we can do is we can define a kernel that is actually going to be an anisotropic kernel. Also, it's not going to be symmetric. Its first entry is R, its second entry is all of my data points. And basically what we say is how close are all of my data points to a reference point according to this local Mahalanobis distance. So in this example up here, if I had a point up here where my mouse is, that would be incredibly far away because sigma is saying, nah, data doesn't really vary in that direction. So a point up there is very strange. Okay? But if I had a point over here, that's normal. So what are the benefits of this perspective? Well, for one, this has what's called a mean embedding. I won't go into the details of mean embedding. There's literally an entire book written about mean embedding distributions. But basically what it is if you just took for each point R, the expected value over all point sampled from your distribution of your kernel. Okay. So this is basically just a function of my reference points. I've now projected a distribution onto my reference points. And I projected it in a way that relates to the local geometry of my data. Okay. And now that I have that, I can define a test. And this is actually basically the equivalent of the kernel MMD test, but now for a much richer class of kernels. Okay. And that test is basically, well, all right, I'm projecting Q onto R. How much do those projections deviate from each other? If they're the same, P is equal to Q. If they're super different from each other, P is completely different than Q. And it has an empirical version as well, which is basically instead of taking expected value, just take a average. Okay. So why does this problem actually give us benefit? Why does this reflect the geometry of our data? How does this tie into the questions that I originally asked? So for one, if I assumed that the family of distributions I was working from really did just come from distributions concentrated on some low-dimensional manifold, how many reference points do I need to cover my data? Well, if the ball is of radius sigma, then I need 1 over sigma to the intrinsic dimension of my data, not the ambient dimension. So already, I've actually made significant improvement because I'm really depending intrinsically. Okay. And by the way, similarly, if I had a tube around my data, so a manifold but plus a little bit of noise or something, it's basically the same number of reference points. And also, the number of reference points doesn't scale with the number of data points. That's really nice. Because if I was just doing just vanilla kernel MMD, and I have, 1 million data points from one distribution and 1 million data points from another distribution, I need to build a 1,000,000 by 1,000,000 matrix. That's really tough, even with that. But in this case, I can have a fixed number of reference points, and I'm good. Okay. The spectral dimension. So first off, if you're on a manifold, the effective rank of this local covariance matrix is basically the intrinsic dimension. So it's killing behavior off the manifold, right? And what it does is it kind of shifts the eigenfunctions around. It pushes functions that vary along the manifold. I'm sorry. I messed up these two things. This should be decreases. This should be increases. Apologies for that. Basically, what it does is it says, okay, if you're varying a little bit along the manifold, that's fine. If you vary tangential to the manifold, that's really bad. Or sorry, normal to the manifold. That's really bad, and that's going to get a very strong weight in my test. Okay. And also, I just want to point out the computational benefit. Let's go back to this question of having n distributions, and we want to compute all n choose 2 distances. If I'm just doing a vanilla kernel MMD, I need to do, well, each test is n squared times the dimension. And I need to do n choose 2 for n distribution. In this problem, if we do this reference point MMD, I only need to compute the affinity to the reference points. So each distribution, I just say, what does it look like on the reference points? That's only n expensive computations. And then that last part was basically just the Euclidean distance, which means that the n choose 2 is only on the number of reference points I have. And so instead of having to do n choose 2 expensive computations, I can do n expensive computations and n choose 2 relatively cheap. Okay. And that's another benefit that you get from making this assumption. So you can prove things about this just as you would prove for any statistics test that you'd be interested in. I'm not going to go into the details of proofs for all of these. Needless to say, they're all basically centered around spectral theory, okay, and eigenfunctions of kernels. But basically what we can say is, all right, if we assume our kernel is positive semi-definite, and that the alternative, in other words, the way that P deviates from Q projects non-trivially onto the reference points we created, and we can give a number of examples where this will necessarily be true, but this is sort of a nice, simple, clean assumption. Okay. Then what you can basically show is if you had a finite number of points from P, a finite number of points from Q, and P and Q really were the same distribution, then your test statistic basically just looks like a chi-square distribution around 0. goes to 0 very quickly. If this is the other extreme, if they were definitely different, P and Q were definitely different from each other, then the test statistic is basically asymptotically normal, and it's bounded away from 0. So you're going to get a non-zero distance. And we get this other category that's kind of fun, which says, what if P and Q are kind of changing as we add more points and we're slowly coming together, but they're coming together at a sort of slow rate? We can establish the rate that they need to stay apart such that we'll still be able to say that P and Q are different. Okay, I won't go too much into the details of that middle case. The first and third are sort of really the sort of classic ways you think about this two-sample test question. But along with that, the other thing that you can show is a power of your test. And you can show actually a non-asymptotic power. So what is a power of your test? Well, it basically just says, all right, what if P was different from Q? You get some distribution. What if your samples were both from P? You get some distribution. If I were to draw some cutoff, what percentage of the time would I mess up one way or the other, right? And what we can show now non-asymptotically is basically this is effectively the amount of time we get it right. So 1 minus that is the amount of time we mess up. The amount of time we mess up and say the wrong thing, these are the same distribution or these are different distributions, decreases like the number of points, 1 over the number of points. So basically, as we get more points, we're going to be certain that we can tell the difference between when two samples came from the same distribution and when 2 samples came from the same distribution. Okay. And all of it winds up depending, not just intuitively, but exactly on the spectrum of our kernel and how the difference of distribution, the difference in densities projects onto the output. That's actually the exact concept. Okay. So this is exactly why if you can, detect small but consistent deviations, you want to give them as much weight as possible. All right. So I'm going to kind of go back real quick to actually let me come down here. I want to emphasize the difference in this spectrum really quick. So let's go back to this original data. You have your blue points, you have your green points. They're consistently deviating from each other, but not by a ton. So what we're going to plot here is basically the kth eigenvalue of several different kernels. The blue is basically for the isotropic Gaussian. That's the eigenvalue of that kernel. The red are the eigenvalues of this anisotropic kernel that I've described. And just for statement, the black are what we call a spectrally filtered version of this. Basically, you don't take the eigenvalue as the weight, but you take some function of the eigenvalue. Okay, you can take like a polynomial of your kernel or something. So these are basically the weights that are going to be associated to each projection of the difference onto the eigenvalue. Okay. And these are actually the projections. For the anisotropic kernel, and this spectrally filtered version of it, the first few eigenfunctions are really the ones that are mattering. Okay, you can see this right here, right? I mean, these are where you're getting the spikes. And we're basically zeroing out a lot of the noise that's going on in the high frequency part. Okay. Whereas if you work with the isotropic Gaussian, you do run into a problem where you get noise going on here and the real contribution doesn't happen until 50 eigenfunctions. Basically, you have a lot of noise you're adding in before you get to the real signal, right? And this is one other thing that I haven't talked about as much. I'll mention it briefly as an extension. But basically, remember in maximum mean discrepancy, there was that function that was the thing that maximized f times p minus 2. That's called the witness function. This is actually a very interpretable function because it's the thing that says where p deviates from q the most. Okay, and you can do that. If G was just the identity, then this would just be this and the witness function of that anisotropic kernel I was referring to. If G is something else, then it's filtered version. But what you can see is that if I look at the witness function for the isotropic Gaussian, you can kind of start to see deviation. It picked up the difference, but look at that. I mean, you've got a lot of issues around where is it really dominant. Okay. you go to this anisotropic version, you get a very clean witness function where you even have a minimal separation going on because that's the the peaks are concentrated apart from each other. And then a filtered version you can do. Okay.
Hey,
all right.
Alex,
Yeah.
Is the witness function a thing you might use for classifying future examples?
Yes, you totally can. Yeah. You can use that as the function that has been learned so that you can then classify.
So it looks like the Gauss witness would be it would generalize poorly compared to
yes,
these
exactly.
alternatives.
That's exactly right. That's exactly right.
Okay. Thanks.
Yep. Okay, so I want to talk briefly about one application of this, and then I want to be able to go to another version of these two distribution tests. Brief application. I mentioned this flow cytometry problem. I just want to give an example. Again, this is where you drop the blood, you get a point cloud for each person. This is the point cloud. This is a 3-dimensional slice of a 9-dimensional object. And this is what one of the point clouds looks like for a healthy person. And this is the same 3-dimensional slice of the 9-dimensional object for an unhealthy person. Somebody that has AML, which is a very deadly type of disease. And you can see these are not things that you can figure out with a t-test. These are very complicated, small deviations. Things like this sharp corner here devolving into a little bit more of a node. This area not being as large here. Okay. So if you just wanted to say, just in an unsupervised question, maybe you just want to say, how far apart are healthy people from sick people? Just give me some clouds, and let's ask the question. Is there more variability among healthy people or more variability among sick people? And are their clusters separated? Okay. So we can basically address this question. And with the anisotropic kernel, what we can do is effectively just pick some reference points around here, build some local covariance matrices in 9 dimensions. And using that test, using that distance, we get all and choose 2 distances. And you can just cluster, there's like a force atlas of that graph. And you can see very clearly the green are all of the people that were sick, the red are all the people that were healthy. You can see very clearly that a lot of the sick people are very, very tightly clustered together. And what you're getting there is exactly that the variation of the point clouds among people that have AML is actually quite contained compared to the variation of health. Okay. And this is if you didn't think about an isotropic kernel, you wind up not being able to detect any of these conditions. Okay. And I want to point out one other thing. This takes, I'm going to say 30 seconds to run on, I'm going to say 10,000 points per person, 400 people, somewhere, 359 people. This takes like 10 hours. So because we have this reference point, it not only makes things better, but it also makes things faster. Okay. And you can do this for other types of deviation, other types of tests as well. There's another type of blood disease, MDS, more broad category of diseases. And once again, you can get some unsupervised questions. Okay. I want to mention very briefly that we've done some extensions of this that I'm not really going to delve into, but these are sort of additional papers if you want to take a look. We've really focused on what you can say about that witness function itself, the thing that I just showed briefly there, right? And we found that if you move to a slight variant of a Gaussian kernel, you can actually prove some really nice Hoffman type results about the convergence of the empirical witness function to the true at a local point. I find that to be, this is sort of a nice way to say, like, all right, that thing we're going to use for interpretation or maybe future classification, it will converge locally. Okay. And that was, sorry, I should have said that was with Rishikesh Maheshwar and Shu Cheng. And then also, just me and Shu, we also worked on this question of what if instead of using a kernel, you used a neural network? Because let's be honest, everyone always says, well, could you do this with a neural network? So we said, sure. And basically what we were able to show was if you have a softmax neural network that's trying to classify points as being from one distribution or being from the other distribution, just a classic classification problem. You can actually get a test statistic out of that. And with that test statistic, what you can do is actually establish a lot of results about how there exists a network with the number of parameters that depends on the intrinsic geometry of your manifold of data, such that the empirical estimate of how far apart they are and the true estimate is going to be like epsilon plus something that's going to go down as the number of points goes to infinity. And we established this for on-manifold behavior, if both P and Q are on the same manifold, and near manifold behavior, which is if they're both within some tube around a manifold. Okay.
Alex, what's epsilon in this slide?
Epsilon is basically a parameter, and that's going to dictate the number of parameters that you need. It's a user-given parameter, and it's going to dictate the number of parameters needed for your network. So this is more of an approximation theoretic type result, but I just kind of wanted to mention that these are sort of some direction. Okay. All right, so I want to mention briefly, just kind of summarize for MMD, what are the sort of pros and cons that we have, because I want to motivate another way that we could approach the problem. So pro, this is a pretty statistical fast convergence. 1 over root n, 1 over n if they're from the same distribution, and that's pretty good. A con is we kind of have this idea of distance saturation. And what I mean is if measuring, MMD is effectively measuring how much deviation there is vertically between the two densities, okay? And as the densities move apart, you're going to kind of saturate. You're never going to be able to get bigger than basically root 2, okay? You know, and what that means is MMD won't be able to tell the blue from the red here versus if the blue is here and the red was off of Mars. They're the same distance apart, they're far. That's not always great. Also, we get, you know, this nice mean embedding and witness function that we can talk about, but a problem is we don't really understand the geometric structure of this latent space. If we were to take a distribution and shift it by a little bit, would the MMD shift like the amount, change like the amount we shift? If we were to rescale the distribution, would it change by the amount that we rescale? Okay. These are drawbacks, right, that I'm admitting to this whole class of work, my own work that I do. But it's still, MMD can be a very useful class. Right? So what I want to do for the next little bit is talk about a different way that we could approach this problem of telling the differences between distributions that actually addresses some of these. Okay. So, you know, pause for a sec, shake it off. MMD, that's this thing over here. Now we're back to this original question, what do you do with this? So, a lot of you have probably seen before the idea of a Wasserstein-2 distance, or an optimal transport distance. So what is it? Well, it's the minimum over all pairings of a point to another point of basically how far you'd have to move sand. You know, if blue was a pile of sand, that's the classic thing. If blue was some pile of sand and red was some other pile of sand, and you were going to move each piece of sand from blue to red, how much work would it take? Okay. So, you know, you move this point to here, that took about distance 3. So that little infinitesimal point of sand had a unit of, you know, it took 3 units of work. Integrate the whole thing up, and this gets you the distance between. Okay. So it's a nice optimal transport result. T is basically all measure preserving functions, basically functions that map, that push you to. So, Wasserstein distance, awesome. It scales correctly with shifts and scalings and rotations, stuff like that. It's really nice. Downsides, it is extremely expensive to compute because you need to do some sort of linear programming or some sort of combinatorial optimization problem in order to find one distance. So if we want to do n choose 2 distances, what do we even do? Okay, you'd have to do n choose 2 optimal transport. I will say optimal transport is very slow statistically. So like if you have a sample from a point cloud, it very slowly converges to the true distance. And this doesn't really inherently generate an embedding, right? I'm getting a distance between 2 points, but how would I do supervised learning with something that reflected Wasserstein? That's the questions that we're interested in. And what I'm going to do is just kind of give the answer briefly, and then we'll talk about why it's the case. So I want to propose, this is again an idea that predates, you know, Caroline and I working on it. I want to propose something called the linearized optimal transformation. If you saw Akram Al-Drubi's talk, it winds up Akram and ourselves wrote papers that were pretty similar that came out within a week of each other on arXiv on a similar problem. So I promise I'm not going to repeat what he said because we have different aim, different scope, a little bit different theory. So I'll just say that. But, you know, this will maybe be similar to what you had seen previously. But basically the idea here, and a lot of this was originally proposed by Gustav Rode, is what's called the LOT embedding. And basically what it says is, you know, in maximum mean or in optimal transport, the thing that's really characteristic of the transport between, you know, of mu is really what is the transportation function that you take to get from mu to somewhere else. Change mu, it changes the transportation. Okay. And so what we're going to do is kind of similar to MMD. We're going to fix a reference. And in this case, our reference distribution is just going to be some distribution sigma. And it doesn't have to be points spread about our space. It can literally just be a Gaussian at the origin. Okay. And the features that we're going to have of mu, we're going to take to be the transport plan that maps sigma to mu. So you have some mu, what's the plan that maps sigma to mu? You have some nu, what's the plan that maps sigma? So each distribution is considered in isolation and compared to a fixed reference. Again, just kind of like in the MD. Well, that is an embedding. This is in L2. So you're embedding into L2. So we could do things like, what is the distance between mu I and mu j in this LOT embedding? Well, it's just basically the Euclidean distance between one set of features and another set of features. What is learning in this case? Well, if we can embed into an L2 space, then we just need to learn a function from L2 into our classification. Okay, so it'd be a function of the transport. Okay, so that is our embedding. Now the question is, what are the families of distributions where we can actually do something? Because I'll say that unlike an MMD where we can just kind of talk about any absolute continuous distribution, now we need to focus in on. So there's some technical details here that I'm not going to go into too much detail about, but what I want to emphasize is basically the following. And the reason I emphasize this is because I'm looking for anyone that would be interested in talking a little bit more about this. So you start at sigma, you have some transport plan that pushes to mu. Say I had some second transformation S that goes from mu to S push forward mu. So think of like shifting mu, scaling mu, shearing mu, stuff like that. When is the optimal transport from sigma to S push mu? When can it be written as pushing the mu and then pushing the S? This is basically the question. Okay. Now, I should note, these two things are always equal to each other. So this term really is S push forward mu. But when is it optimal? That's the question. When was it the optimal transport? Okay. In D equals 1, it's straightforward because, well, I shouldn't say straightforward. There's a great paper that Gustavo wrote about this, but it's basically there's only one measure preserving function. So things become a little bit easier. If you find it, it is optimal. In greater than 1, you have this problem that comes down to basically showing that you have convexity of the gradient of your transport plan can be written as the gradient of some convex function. Okay. And effectively, this whole problem of finding S's that are useful to us comes down to this equation right here. When can I compose S with the gradient of a convex function and get the gradient of a convex function? That's the question. And that's a hard question. And I would love to see more about that, right? I'm sure I know that this somehow relates to basically like when is the commutator of the gradient and the S equal to 0? There's this issue of convexity here that I'm not 100% sure how to address. The only way that I can talk about it is to give examples of when this is true. Okay, so if you shift the distribution, that statement is true. Okay.
Do you want S to satisfy this for all gradients, that it maps all gradients to gradients?
No, that if you have this, it kind of does have to be that. It's basically your transport plan can be written as the gradient of a convex function.
Yeah.
And when you push it in, you have to get the gradient of a different convex function.
So it's not for a particular phi that S does this, but for
this
every
is the
phi?
thing, it might be. The ones that I'm going to talk about are independent of phi.
Okay.
Or independent of phi, independent of sigma. Yeah, I mean,
Okay.
as long as they're convex.
Great.
Okay. So shifts do this. You have any gradient of a convex function, you compose it with a shift, you can write that as the gradient of a different convex function. Scaling do this. Affine transformations do this. Are there more, or are these the only ones? That's really a question that I'm kind of curious about. Okay. But a second thing that I want to address, and by the way, this is another place. This is a place where the talk from Mark from a couple weeks ago and what we did deviates a little bit. I want to think not just about shifts and scaling and affine transformations, these rigid transformations of mu. I want to think about perturbations. What if I had an almost shift? So I moved something, but twisted it a little, right? An almost scaling, a little bit of a shear. These are going to be perturbations that we can talk about, okay? And we can write down all perturbations of shifts and scalings and affine transformations, okay? And that's basically any function in L2 such that if it was a shift, scaling, or affine transformation, G minus, there is one such that G minus F. Okay. And the family of distributions I'm going to consider is that. Take a mu, create all shifts, scalings, perturbations of that. That is my distribution. Okay. So real quick, I just want to establish what we can say about this and why it's actually pretty useful. Okay. So first off, I won't get into the assumptions too much, but basically we can say something about the unsupervised result. So we wanted to be able to say something about the optimal transport between some push forward of mu and some other push forward. These are two different distributions. Okay, how far apart were they? Well, it winds up, this is the cheap way we can do it, right? Create an LOT embedding of one, create an LOT embedding of the other, take Euclidean distance. Those distances are bounded between 0 and are basically Hall their 1/2, where the epsilon is related to how much of a perturbation we're considering. Okay, so if you don't allow for perturbations, if you only allow for shifts, scalings, and affine transformations, these two things are in isometry. That was, I mean, I'm not gonna lie, that was surprising to me when we first found it. Okay, but on top of that, if you do have perturbations of stuff, you're not messing up the distance too much. It only scales like epsilon. So again, this gives us this beautiful problem where instead of computing n choose 2 distances between all of our shift scalings, affine transformations, perturbations, mu, really all we need to do is compute their n optimal transports to a fixed sigma, and we basically got it because we can compute the distance matrix really easily, and we'll only have a little bit of error. Okay, and once you have the distance matrix, you can do whatever, clustering or embedding, whatever you want. And by the way, this actually works in reality. So, here's like a distribution, which is like the distribution of these points on the unit square. You shift it around and you compute the LOT distance and you compute the actual Wasserstein distance, and you get literally 0 error. Okay. You do some perturbations, which is like rotating one a little bit. And the error between your LOT and your perfect Wasserstein distance decays or grows much more slowly than epsilon root of.
So what's epsilon in this slide? Sorry.
Oh, epsilon is basically how much of a perturbation we're applying. So how far away are you from the shift?
Yeah.
How far away are you from the scale? Okay. So in this case, you're pretty far away because you've done a 45-degree rotation. That's significant. Okay. But the error doesn't grow that much, and we can write down these constants explicitly. Okay. And one more thing that I want to mention real quick, and I apologize because I'm running a little late, so I'm just going to mention this very briefly. Another way to talk about these shifts and scalings is you could call them that the LOT is compatible with the action that we're doing, compatible with shifts, compatible with scalings. In other words, that sort of gradient type equation I was referring to is satisfied. So there's some nice little proofs that you can have here that basically says if your set of shifts was a convex set and compatible, then when you embed into LOT space, your embedding is a convex set. And if it's almost compatible and convex, then your LOT embedding is what's called 2 delta convex. Basically, it's convex with a little bit of a tube around the edge. Okay. So what do you have when you can embed something into a convex set? Well, if you had some family of distributions and some other family of distributions, and they both embed into a convex set, as long as those convex sets don't overlap, harmonic guarantees I can build a linear separator between them. Okay. And by the way, in this perturbation case, you need a little bit more than disjoint. You need some minimal separation. But so that just says if these two sets are a little bit apart, when you embed them into LOT space, they're still a linear classifier. Okay. And we can be very explicit about what that is when you're working with shifts and scalings. Exactly what the constants are, exactly how much error you and I just want to show one last example of why this is useful. Let's take an experiment. Sample a bunch of 1s and 2s from MNIST. But we're going to make an augmented data set. Rather than just grabbing a 1 and using it as my training data, I'm going to apply an arbitrary rescaling and shifting of that number, random. Okay? So now I have a 1 up here, and a 2 down here, and a huge 2, and a tiny 2, and all these things. And that's my training data. So I sample K points from my training data from each class. I do this LOT embedding, and then in LOT space, I build a linear classifier. This is the error of that classifier as a function of the number of training points I have. And this is our LOT. This says, if I get 60 examples of a 1, and again, these are much more complicated ones. They're shifted, they're scaled. I get 60 examples of a 1, 60 examples of a 2. My testing error on, I think it was 1,000 new points, is under 10%. If I have 80, it's under 5%. And by the way, if you did this with PCA, if you just embed those points using PCA and then try to build a linear classifier, you're completely out of luck. You're not going to learn. Okay. And this is just a visualization of what this cloud actually looks like. Right? You get a really nice linear separation in LOT. So again, I mean, this is another problem where comparing distances and learning on distributions, I think, is a pretty interesting problem. There's a lot of rich math here that you can get into. There's this algebra part to it that I'm honestly, this is not my forte. So if anyone knows about other types of rigid transformations and shifts and scalings that are going to satisfy some of those conditions, that would be awesome, right? And we're sort of looking into this now. A couple of current drawbacks, even just computing each of those n embeddings is expensive because you still have to solve an optimal transfer problem. We're working on an approximation of this. Similarly, what happens when you move beyond just an epsilon perturbation? Are there additional, ways that you can perturb mu and get something nice? This is the direction I'm going as well. Went a couple minutes over, I apologize for that, but yeah, there you go. Any questions?
All right, thanks for the talk. Be sure to use this reaction icon to express your appreciation, and we'll stop the recording.